Okay, this is part one of my screencast covering general relativity. That's for the PowerPoint presentation that accompanies my lecture. Please make sure, however, that you watch my lectures on general relativity prior to viewing this screencast. The reason for that is because I will be doing this material or covering this material rather quickly here in the screencast. I go through it in more detail in lecture. Okay, as I do mention in lecture here, Einstein publishes general relativity basically at the end of 1915, early 1916, and Einstein's theory describes gravity not as a force, but instead as geometry, the curvature of space and time that is caused by the presence of mass. As described in lecture, general relativity is an elegant, beautiful theory that describes the universe at large scales. Okay, this right here is a simple depiction of a gravity well. Gravity well pictures such as these are somewhat misleading. Usually the way that this is depicted, and I demonstrate this in lecture, is by taking a two-dimensional surface and then curving it with the presence of mass into a third spatial dimension. What's really happening, however, is that three-dimensional space is curving into a fourth spatial dimension. That fourth spatial dimension is hyperspace, also called Hilbert space, and it's equal to the speed of light multiplied by the time t. The width and depth of the gravity well itself is dependent upon the mass, size, and density of the object that is causing it. Okay, and then with the theory itself in its publication, Einstein, as I mentioned in lecture, provides his first proof of the theory, which has to do with the precession of Mercury's orbit. As Mercury orbits the Sun in an elliptical orbit, the entire ellipse itself is precessing or swiveling around the Sun. Newtonian gravitation does not provide a satisfactory explanation for why this is occurring. Ultimately, the explanation comes from general relativity through a process referred to as frame dragging. Basically, as the Sun rotates, it more or less drags space-time along with it. This then results in the precession of Mercury's orbit. The clinching evidence, however, of general relativity came in 1919, a couple of years after the publication of the theory, with the event of the solar eclipse that occurred in May of that year. Okay, now the solar eclipse itself is not really that important, but when the moon is blocking the sun's light, this then allows you to look very carefully at the area right next to the sun. So for example, we have here the eclipsed sun like so, and then right over here is the Earth. And then in the background, right over here is the actual location of a background star. We already know what it is from mapping it out earlier. But then as the light from that star passes by the sun, it passes through curved space. And then therefore, ultimately, if we're standing here on the Earth, we then look off in this direction like so, see the apparent position of the star. So the star appears to be further away from the edge of the sun than it should be. This particular observation was confirmed in 1919 during the solar eclipse. This is basically more or less experimental proof, if you will, that Einstein's theory is correct. When this result was published in the world's newspapers in 1919, it turned Einstein into a media star. Okay, the situation itself that was depicted in the previous slide is an example of what is called a gravitational lens. We actually see examples of gravitational lenses throughout the entire universe. So right here, for example, all of this yellow stuff that you see right here is actually an enormous supercluster of several thousand galaxies. There's a huge amount of mass that is contained here within this region. But then in the background, much further away than the cluster itself, is a single background galaxy. And then light from that background galaxy, as it passes by all of this enormous amount of mass associated with the supercluster, well, that light then passes through curved space. This then results in multiple images of the background galaxy, and you can see multiple images of that background galaxy as these highly distorted looking thin lines or thin blue lines here of images. Okay, now the geometry itself of this supercluster of galaxies is amorphous. It's kind of distributed unevenly. This then results in essentially the distortion of the background galaxy's light as it passes by that foreground cluster. And then ultimately here over the Earth, for example, you see then multiple images of that galaxy surrounding the cluster itself. Here's another nice example of that here. In this photograph, this is a different galaxy cluster than the last one, but here is that foreground cluster, and then in the background is a much further away background galaxy, and you can see multiple distorted images of that galaxy here. Okay, moving on to black holes. So in 1916, just a couple of months after the publication of Einstein's theory of general relativity, Carl Schwarzschild, a mathematician, used the Einstein field equation to work out a mathematical solution that resulted in the following type of an object. He discovers an object, a mathematical solution to the equation, that is a point with infinite density. The point itself is referred to as a singularity. Geometrically, that point of infinite density is represented by an infinitely deep gravity well. This then results overall in the object that's referred to as a black hole. Okay, now if you were out in the universe, you can actually look at a black hole. The black hole itself would appear to be spherical. And then what you are looking at right here is a horizon, an event horizon. It's also called the Schwarzschild radius. I described the calculation for the event horizon in a couple of my physics classes, Honors Physics AB and AP Physics C. But remember from those classes that essentially what the event horizon is the following. If you were closer to the singularity than the event horizon, you would need to have an escape velocity greater than the speed of light. So then therefore, if you were much further away from the black hole and you then look in this direction, the reason why you see this perfectly featureless black sphere is because you are literally looking at a horizon, a point beyond which you cannot see. Okay, now as I described in lecture, there is a nice allegorical story called Flatland that allows you to visualize exactly why the black hole's event horizon would appear to be spherical. Essentially what you're looking at is a four-dimensional object, but you're looking at it in three-dimensional space. So in the allegorical story of Flatland, we have a two-dimensional universe, and a character in that universe is called a square. And then over the course of the story, a three-dimensional sphere passes through Flatland. The inhabitants of Flatland become aware of the third dimension because as the sphere itself is passing through Flatland, people in Flatland or the characters in Flatland would see a point, expand out to a circle, and then collapse back down to a point as the sphere itself passes through the plane. So Flatland provides a nice allegorical way, if you will, of visualizing a fourth spatial dimension, even though we only see three-dimensional space around us. Okay, right here is an actual photograph of a black hole. This is the black hole that's at the center of the huge galaxy M87 at the center of the Virgo supercluster. This right here is actually a radio image of the black hole, and the black hole appears exactly as the theory predicts. Okay, let me go ahead and pause this here as part one of this screencast covering general relativity.